You think light travels. You do. A little ball of brightness leaves the sun, flies in a straight line, lands in your eye 8 minutes later. You have carried that picture since you were a kid, and you've never, not once, questioned it. The picture is wrong. A photon does not go from A to B, the way you imagine anything going anywhere. I mean anything. What it actually does is so strange that Richard Feynman won a Nobel Prize describing it and still called it absurd. His word, absurd. And by the end of this video, you are going to owe every window in your house an apology. Let's start with what you were taught, because it works. It works beautifully. And that is exactly what makes it dangerous. Light travels in straight lines. It bounces off mirrors at matching angles. It bends when it enters water. Every rule you learned in school predicts shadows, lenses, laser beams, all of it. Engineers build telescopes with those rules, and nobody is calling them useless. Works is not the same thing as the truth. In the 1600s, a French lawyer, named Pierre de Fermat, noticed something the rules were hiding: the straight line through air, the sharp bend into water, the bounce off a mirror. Every path light takes is the path that takes the least time. Out of every route light could possibly take between 2 points, it always takes the fastest one. Now that sounds tidy. It should horrify you. Because when you say light takes the fastest path, you are quietly claiming that it compared the options. Feynman had this famous way, this wonderful way of exposing how weird that is. Picture a lifeguard on a beach, and out in the water, off to one side, a swimmer in trouble. The lifeguard runs faster on sand than she swims in water, right? So her fastest route is not the straight line. The straight line wastes precious seconds in the water, where she's slow. The smart move is to run further along the sand and bend her path at the shoreline. Trade slow swimming for fast sprinting. A good lifeguard does this instinctively. She looks at the options, she judges them, she chooses. Light bends at the surface of water in exactly the same way, by exactly the amount that minimizes its total travel time. But light is not a lifeguard. A photon has no eyes, no brain, no map of the pool. It cannot survey routes it did not take. So explain the mechanism to me. How does a thing with no mind test paths it never travels and reject every single one of them except the winner before it has moved anywhere at all? You can't. Nobody could. For 300 years, the sharpest minds in physics used least time to calculate everything and quietly avoided asking how light pulls it off. And light was hiding an even dirtier secret. In your living room window, stand in a lit room at night and look at your window. You see the room reflected faintly in the glass and the dark street through it. Some light bounces back, some goes through. Measure it with single photons, and the number is stubborn. Out of every 100 identical photons that hit a sheet of glass, about 4 reflect off the front surface. The other 96 sail straight through. Identical photons. Same energy, same source, same angle, same glass. 4 bounce, the rest pass. And Feynman asked the question you should be asking. How does a photon make up its mind? Newton wrestled with this exact problem, and he lost. He guessed the glass had tiny, invisible imperfections. It doesn't. Polish the glass to absolute perfection and the 4% stays. Then it gets insulting. Bring the back surface of the glass into the experiment and the reflection refuses to sit at 4%, depending on nothing but the thickness of the glass. It cycles anywhere from 0 to 16%. 0 to 16. The front surface of a piece of glass reflects differently depending on how thick the glass is behind it, as if the photon checked the depth of the whole pane before deciding whether to bounce off the front. By every rule you were taught, that is impossible. So the rules you were taught are not the rules. And that window has earned the apology I promised you, because it has been showing you quantum mechanics your entire life while you looked through it at the weather. Feynman's answer is the reason this video exists, and I need you to resist the urge to soften it into a metaphor. Stop asking which path the photon takes. It does not take a path. To calculate what light does, and this calculation matches reality every single time, you must account for every possible route between A and B, the straight line, the wide detour through the corner of the room, The ridiculous zigzag that visits the far side of the lamp, every last one of them. Each path gets a little arrow, and you can picture that arrow as the hand of an impossibly fast stopwatch spinning while the light moves along that path. The moment the path ends, the hand freezes. Now collect the frozen arrows from every path and add them together, head to tail. The distance they cover squared, that is the probability the photon arrives. That's it. That is the entire theory. And watch where your straight line comes from. On the wild looping paths, tiny changes in the route swing the travel time massively. So their arrows freeze pointing in every direction and they cancel each other into nothing. But near the path of least time, neighboring routes take almost exactly the same time. Their arrows freeze pointing the same way. And they stack so the straight line turns out to be the last man standing. The sole survivor of a war where every other path canceled itself out. Feynman put it in writing. Light refuses to travel only in straight lines. It smells the neighboring paths around it, sampling a small core of nearby space. The lifeguard question just dissolved. Light never chose the fastest route. It took every route. And the fastest one is where the arrows refuse to cancel. If your picture of reality just cracked, good. That means you're paying attention. I break one comfortable assumption like this every week, so hit subscribe before you forget. Now let me prove those ridiculous paths are physically real. If light truly sniffs every path, then the off-angle paths must exist, and a mirror should be able to betray them. Look at a region far off to one side of a mirror where the equal angles rule says no reflection belongs. The arrows from that region spin through wildly different times. They freeze pointing in every direction and they cancel. Nothing reflects from there. So far, the classical rule looks safe. Now do something vandalous. Mischievously, scrape away only the strips of that mirror whose arrows point the wrong way and leave the strips whose arrows agree. You have destroyed half the surface, and the forbidden part of the mirror lights up. Reflection appears at an angle where reflection was never, ever allowed. In his book QED, Feynman could barely contain himself about this one. Isn't it wonderful, he wrote. You scrape part of a mirror away, and it starts reflecting. That scraped mirror has a name, a diffraction grating, and you already own one. Tilt the back of a CD or a DVD under a lamp and watch the rainbow crawl across it. Every one of those colors is light arriving along a forbidden angle, because the grooves silenced the paths that used to cancel it. The rainbow on a disc is a photograph of the paths you were told light never takes. And once you allow every path, you have to allow everything about those paths. Feynman went further than most textbooks will ever dare to follow him. In the same theory, there are arrows for light moving faster than light speed, and arrows for light moving slower. Over any decent distance, they cancel each other so thoroughly that only one speed survives. But over very short distances, they genuinely matter. So take stock of what's left of your childhood picture. The little ball, gone. The single path, gone. Even the one sacred speed only survives as the winner of a cancellation. Nothing travels the way you meant the word. What exists is something that explores everything inside a universe that only ever shows you the sum. Now, if you're waiting for me to shrug and call this quantum mumbo-jumbo that nobody can truly grasp, you'll be waiting a long time. That is not mysterious. That is magnificent. This description of light is the most precisely confirmed idea our species has ever produced. When physicists compute with these little arrows and then measure the electron to check, theory and experiment agree so closely that Feynman compared it to measuring the distance from Los Angeles to New York and getting it right to the width of a single human hair. One human hair across a continent. So look again at the most boring optical event of your day. A sunbeam crosses your kitchen floor. Inside that dull, straight, obedient beam, every possible route between the sun and your floor was accounted for. An infinity of journeys interrogated and canceled, and the beam you see is the silent verdict. You were staring at one of the deepest computations in nature and calling it a sunbeam. Feynman never asked you to find any of this reasonable. He asked for something harder. He asked you to accept nature exactly as she is. And knowing how the trick works does not shrink the magic. The straight line you stopped questioning as a child turns out to be the visible edge of everything light tried. You did not lose a simple world today. You traded it. You traded it for a much bigger one. By the way, your head is aging faster than your feet right now. And time itself bends for the same kind of reason you just watched light bend. That video is on screen now. Click it.